So here's an RLC series circuit that has some numerical values that we can use as an example problem. We're told that the resistance is 5 ohms, the inductance is 9 millihenries, and the capacitance is 2 millifarads. Actually, before we solve this example problem, let's backtrack and just do a little review of everything we know about the behavior of an LRC series circuit that's driven by a generator. We know that the current is going to vary sinusoidally. So if we were to graph current versus time, we get this oscillatory behavior. And whether or not we want to express it as instantaneous current is max current times sine of omega t, or instantaneous current is max current times cosine omega t, really depends on where we put our origin in time. So for example, we could put our origin here, and then the graph would actually be I equals max current times negative sine omega t. Or, if we wanted, we could put the time axis, the time equals 0, the y-axis here, and then we would have this expression. So let's do that. Let's consider this to be time t equals 0. Okay. What other equations can we summarize here? The inductive reactance is omega times L. The capacitive reactance is 1 over omega times C. The maximum voltage across the inductor is the inductive reactance multiplied by the max current. The maximum voltage across the capacitor is the capacitive reactance multiplied by the maximum current. The instantaneous voltage across the inductor is equal to negative omega L I sine omega t. The instantaneous voltage across the capacitor is I divided by omega c sine omega t. The impedance of the entire circuit is equal to the square root of r squared plus the difference between inductive reactance and capacitive reactance, quantity squared. We can find the phase angle using the equation tan phi is equal to, the difference between the inductive reactance and the capacitive reactance divided by the resistance. Okay, let's see. There may be some other equations we want to recall as we solve this problem, but there's some good starting review. Oh, I guess we should also draw one more thing, the Phasor diagram. So we'll make a green vector to represent the current phasor. Purple vector represents the voltage across the resistor. If you recall the mnemonic Eli the Iceman, then you know we can put the vector that represents the voltage across the inductor 90 degrees ahead of the current, and the vector that represents the voltage across the capacitor lags by 90 degrees. And if all of these vectors are rotating together as one, then it represents a sort of phasor diagram. Let me label each of those vectors one more time. That's the voltage across the inductor, voltage across the capacitor, and voltage across the resistor and the current. The instantaneous value, the length of the vectors is the instantaneous value. Is the maximum value, and their instantaneous values are found by taking their projection onto the x-axis. So you could imagine if this whole phasor diagram was rotating, then all of the lengths remain the same, but their projections onto the x-axis are continuously varying. So, on to the problem at hand. First question, what's the value of the inductive reactance? Inductive reactance is equal to frequency multiplied by inductance. Oh, and we're given a frequency of 60 hertz. Now careful, omega is frequency in radians per second. Any expression of frequency in hertz is just standard frequency f. The relationship between these, omega is 2 pi times f, because there's always 2 pi radians in any given cycle. So frequency is in cycles per second. Angular frequency is in radians per second. We can relate the two in this manner. So first of all, let's figure that out. So omega would be 2 pi, and what we really mean is 2 pi radians per cycle, multiplied by 60 hertz. By hertz we mean cycles per second. So you see cycles cancel out and we're left with radians per second. Grab a calculator and see what you get. So when I multiply this out, I get about 377 radians per second. And this is a common value. The frequency of 60 hertz is the frequency of AC we have from our household outlets. So if you want to, you can think of it as 377 radians per second. So our answer to number 1, let's write it in below. The inductive reactance is equal to 377 radians per second multiplied by, what's the inductance? 9 millihenries, or 9 times 10 to the negative third henries. So this comes out to about 3.4 henries per second. Notice we ignore the units of radians, and a henry per second is the same thing as an ohm. Number 2, what's the value of the capacitive reactance? Capacitive reactance is 1 divided by angular frequency times capacitance. So in this case, it's 1 over 377 times 2 times 10 to the negative third. Of course, I mean 377 radians per second, and 2 times 10 to the negative third farads. And this gives a value of about 1.33 ohms. Okay. What's the value of the overall impedance? The impedance can be found by taking the square root of resistance squared plus the difference between inductive reactance and capacitive reactance quantity squared. So we plug in the given values. Resistance was given as 5 ohms, so this is the square root of 5 squared plus 3.4 minus 1.33 quantity squared. And we get about 5.4 ohms. Okay, moving on. What's the maximum amount of current? Well, we can just use Ohm's law. The maximum current is equal to the maximum voltage divided by the impedance. So maximum voltage is 170 volts, and that's also a common value. Again, these are the values of the AC electricity that we have in a standard household outlet. 170 volts peak value at 377 radians per second corresponds to an RMS voltage of 120 volts and a standard frequency of 60 hertz. So you're probably more familiar with these expressions for household, but they correspond with the values shown above. So 170 volts divided by 5.4 ohms gives 31.4 amps. Now the RMS value of any oscillating quantity is just found by taking 2 over pi multiplied by the maximum value. So if we do 2 over pi multiplied by 31.4, we get a value of 20 amps. We could have just as well used Ohm's law and said the RMS current is equal to the RMS voltage divided by the impedance. And so 120 volts divided by the 5.4 ohms. Well, I think we've got a little bit of a rounding issue here, but I probably should have kept more sig figs, but this is approximately 20 amps as well. Okay, moving on. Same circuit, same values. What's the resonant frequency? So this is definitely not in resonance. If we drive a circuit like this at 60 hertz, we find that the inductive reactance of 3.4 ohms is greater than the capacitor reactance. And if that's the case, then we know the frequency is higher than resonant frequency, because with a greater reactance for the inductor, you're going to have a greater maximum voltage across the inductor. So the Phasor diagram would look like this one. There's voltage across the resistor, voltage across the inductor, a smaller amount of voltage across the capacitor, and so this would reduce down. I could leave the voltage across the resistor alone, and I can combine the voltage across the inductor and the voltage across the capacitor into a single vector equal to the difference between the two, and then you can see the resultant of these leaves you with some non-zero phase angle. So the only way you achieve resonance is if the EMF is in phase with the voltage across the resistor, and so the phase angle would have to equal 0, and that could only happen if the voltage across the inductor and the voltage across the capacitor were equal, so that they cancel each other out. So when would that happen? Well, as long as the inductive reactance and the capacitive reactance are equal, then this is the sort of Phasor diagram you'd be left with. So let's see, let's move our work down to here. This would mean that omega L, that's how we find the inductive reactance, would have to equal 1 over omega C, that's the capacitive reactance. So let's cross multiply and see what we get. That means omega squared is equal to 1 over LC, or in other words, the frequency that leads to resonance is the square root of 1 over LC. So let's call that omega naught. And that's the symbol that we'll refer to as the special frequency, known as resonant frequency. So given the values we have in this example problem, our resonant frequency would be equal to 1 over the square root of, 9 millihenries, or 9 times 10 to the negative third, and 2 millifarads, 2 times 10 to the negative third. Okay, try that on your calculators. And this comes out to 235.7 radians per second. And the question says, state the resonant frequency in terms of omega. In other words, what's the number of radians per second for the resonant frequency, but also what's the number of cycles per second, what's F. So again, recall that angular frequency is 2 pi times standard frequency. So turn that equation on its head. Standard frequency is angular frequency divided by 2 pi. So if we divide 235.7 by 2 pi, we get a frequency of 37.5 cycles per second, better known as a hertz. So these are equivalent 235 radians per second corresponds to 37.5 hertz. Both of those would be a way of stating the resonant frequency. Let's find the phase angle. Phase angle can be found from the formula tangent theta is equal to inductive reactance minus capacitive reactance divided by resistance, or if we want to be exact, omega L minus 1 over omega C divided by R. So let's compute that down below. Omega L. 377 radians per second. Or here, how about this? Omega L minus 1 over omega C over R. Let's get rid of any rounding issues and sig fig problems. So omega is the same thing as 2 pi f. So we can say 2 pi f times L minus 1 over 2 pi f times C, all divided by R. So we have 2 pi times 60 times 9 times 10 to the negative third minus 1 over 2 pi times 60 times 2 times 10 to the negative third. Hopefully you can read that. Good thing I'm narrating. Divided by, what's the value of R? Oh yeah, 5 ohms. Okay, let's plug away in our calculators here. Okay, this comes out to something minus 1.326. There, I'll keep a lot of sig figs in the work. This is 3.393 divided by 5. Okay, so we get tangent phi is equal to 0.41, so that means our phase angle is about 22.45 degrees. If you want to convert that to radians, then we can multiply by pi and divide by 180. So it's just as well to say the phase angle is equal to 0.39 radians. Oops. Where'd we go? 0.39 radians. Either one is acceptable. Okay, what's the maximum voltage across each circuit component? The maximum voltage across the inductor is the inductive reactance times the maximum current. So if we scroll back and look, our maximum current is 31.4 amps, and our inductive reactance is 3.93 ohms. I'm sorry, 3.393. 3.393 ohms multiplied by 31.4 amps. Double check that one more, yep. And that comes out to 106.5 volts. The maximum voltage across the capacitor is capacitive reactance times maximum current. So this is 1.326 ohms multiplied by 31.4 amps. And that comes out to 41.6 volts. The maximum voltage across the resistor is the resistance times the maximum current. So this is 5 ohms multiplied by 31.4 amps. This gives us 157 volts. Okay, so number 10, true or false, if I add the maximum voltage across the resistor plus the maximum voltage across the inductor plus the maximum voltage across the capacitor, does that equal 170 volts? Kind of seems like it should, right? My generator has a max voltage of 170 volts, and then I've strung an inductor, a resistor, and a capacitor together in series, so it seems like by Kirchhoff's loop rule, if I take the maximum voltage across the inductor, 106.5, plus the maximum voltage across the resistor, 157, plus the voltage across the capacitor, 41.6, but clearly those do not add up to equal 170, so what gives? Well, these devices all operate out of phase with each other. So you'll never have the maximum voltage across the inductor at the same moment in time that you have the maximum voltage across the resistor. So this is not a correct statement. So number 10, the answer is most definitely false. However, the instantaneous voltage across the inductor and the instantaneous voltage across the resistor and the instantaneous voltage across the capacitor do have to add up to equal 170. In fact, the way the maximum voltages add is like this. The voltage across the source should be equal to the square root of the voltage across the resistor plus the difference between the maximum voltage across the inductor and capacitor, quantity squared. So let's see if this works out. 157 squared plus the difference between 106.5 and 41.6 quantity squared. Grab a calculator, let's see what you get. 106.5 minus 41.6 squared is equal to 4,212. 157 squared is equal to 24,649. So we need to take the square root of 28,861. And sure enough, that's equal to 170 volts. Okay, so hopefully this example problem sheds a little more light on all of the equations we've been deriving for the behavior of the RLC circuit. And you ask, why is the LRC circuit important? Well, you can't make a circuit without having a resistance to it. Even bare wire has some amount of resistance, right? So if you try to design an electric circuit and say, I'm only going to include an inductor and a capacitor, so I don't really know, the wire itself has to have some non-zero amount of resistance. So in all practical circuits, there's a resistance you can't avoid. Can the same thing be said about inductance? Yeah, absolutely. You say, I'm going to try to make a circuit that only has resistance and capacitance. Well, you can't make a complete circuit without at least having one loop. And when current flows through a loop, it behaves like an electromagnet. But it imposes flux onto itself, and so there is a form of inductance just by virtue of having at least, every circuit is always at least one loop. So there's always some non-zero, albeit might be very small, but there's always some non-zero amount of inductance. So the bottom line is you can't really avoid these quantities in electric circuits. So knowing how they behave when powered by generators or by sources of AC is important, because this is how we power all of our homes and businesses. The reason we choose to power with AC instead of DC is AC's ability to be transformed. We can step voltages way up at power plants and step them back down at the house, and therefore avoid energy loss in the transmission lines by transmitting the electricity at high voltage and low current. So there you have it. We'll do a couple more example problems to try to illuminate what all these equations mean.